and also to my co-authors, Avneesh, Chris, Dyer, and Eric. So just as a quick overview, this paper is about a novel technique for language modeling using ensembles of low-rank matrices and tensors that essentially can be thought of generalizing existing n-gram techniques to non-integer n. And empirically, we consistently outperform state-of-the-art Knaser-Nye baselines for the same context length. And we can do this computationally in a way that doesn't sacrifice the advantage of n-gram models. In particular, you don't need partition functions or normalizers, so you have fast evaluation at test time. So the goal of language modeling, seemingly very simple. You just have to evaluate probabilities of sentences. So I get a sentence, like linear algebra is awesome, and it has a certain probability. And then I get another sentence, linear algebra is boring, and I hope that it has a lower probability. And it's very useful in a lot of downstream applications like MT and speech recognition, where you need to evaluate the score of a lot of different phrases. And n-grams are very simple, but they're the predominant approach to language models. And so for this talk, we're going to have a vector, which is going to represent the unigram, where this is the count of the current word. The diagram will be a sparse matrix, where the little purple dots are the non-zero entries. And this will be the count of the word in the previous word. And the trigram, which is even sparser than the bigram, is going to be the word in the previous two words. And as you can see, as the n-gram order increases, so does the data sparsity. In fact, it can get, this has like 10 to the 15 parameters, 10 to the 10. And so to alleviate the data sparsity problem, the common technique is to use smoothing, where I first look in my trigram, and maybe I see a 0. And so then I back off to my bigram. And if I still see a 0, then I back off to my unigram. And n-gram models are very effective because they have a very fine to coarse structure. They can capture various levels of dependence in language. So my trigram can have very specific phrases like New York City. My unigram captures very coarse level things like the is maybe more popular than n or something like that. They're very fast. They have O(n) test complexity where n is the n-gram order. And low context sizes like 3 or 4 are sufficient to get good results, which is important in applications like MT, where like decoding depends exponentially on the context length. The classic disadvantage of n-gram models, which a lot of approaches in the past decade or two, like class-based methods or neural nets have looked at, is that there's essentially no notion of similarity among words. So if I want to measure the probability of a phrase, house given decrepit, decrepit is maybe a rare word, doesn't appear in the corpus. And so the n-gram is forced to back off to house. But what you would really like to do is use these other related words and back off to some coarser grained model, which is house given a synonym of old. And this provides a very nice motivation for low-rank methods, where I had a sparse matrix, and I can take a low-rank approximation to get something dense. And now words with similar contexts will have similar projections, like house, cabin, flat, and old, shabby, decrepit. And this seems nice, and low-rank approximations are very successful in ML, like in Netflix especially. But people have tried these in language modeling since '97, and they're not very successful. They don't outperform state-of-the-art Knaser-Nye baselines. So in this talk, we're going to conjecture that the problem is essentially that low-rank methods are operating at some level of fixed granularity, where I pick a rank that determines my amount of smoothing, and if my rank is too small, then specific phrases that were actually quite happy in the sparse bigram now get diluted probabilities in the low-rank bigram because I'm kind of taking all these synonyms and I'm not capturing the specific phrase itself. And on the other hand, if I have a very large rank, then I'm not doing very much smoothing, so very rare words don't get accurate estimates. So our approach is going to be to try to take the best of both worlds. We're going to construct ensembles of low-rank matrices and tensors to model language at multiple granularities. And our approach is going to include existing n-gram techniques as special cases, like absolute discounting and Knaser-Nye, which is different from previous low-rank approaches which tried to do something orthogonal. And it's going to computationally preserve the advantages of standard n-gram approaches. It will be effective for short context lengths, and it will have fast evaluation at test time. So I'm first just going to present a brief outline, a background on Knaser-Nye, because then we're going to generalize specific aspects of Knaser-Nye to our approach. So the intuition behind Knaser-Nye, which is essentially the state-of-the-art n-gram model, is that if I have a bigram and a unigram, I'm only using the unigram when I back off from the bigram. So in some sense, I should be changing this lower order distribution to condition on the fact that I've backed off. And so consider two words, York and door. York follows very few words like New York. Door follows a lot of words, the door, red door, my door. And so this means that if I backed off, I probably had some rare hit context. And the subsequent word is much more likely to be door than it is to be York. Because if it was York, I had very specific phrases, and I'm much more likely to have some unknown context appear here rather than with York. And mathematically, you can write this as the probability of door, given the fact that I backed off, is greater than the probability of York, given the fact that I backed off, independent of the actual marginal probabilities. Or not independent, but different than the original marginal probabilities. And I'm going to represent this alteration with this color change. So Kneser mathematically defines this notion using this. Essentially, it counts the number of unique words that precede WI, which is the diversity of WI's history, which is this n minus quantity. And the Kneser unigram is defined as the normalized version of this. And now I have this bigram, and I have this altered unigram. So now I just need to put them together to make an ensemble. Kneser does this with fixed discounting, where you subtract a fixed discount d from all the counts. And now this conditional sums to something less than 1. So I can reassign the probability mass from the bigram to the Kneser unigram, where gamma is the leftover probability to reassign. So the key thing that makes Kneser so successful is that essentially the lower order marginal aligns. So I've smoothed my bigram estimate, and it's no longer the MLE, or the max likelihood. But when I marginalize out WI minus 1, then what I get is still the empirical unigram estimate, or the MLE, where I've used this hat to be empirical. And the reason I've gone through all of this is that our goal is going to be to generalize these different aspects that I've discussed to our scenario. So first I'm going to talk about what our ensemble is actually made of. Kneser uses these unsmoothed n-grams. And this is where we're going to talk about rank. So the empirical bigram in general is full rank. But if I know that WI and WI minus 1 are independent, then the probability factorizes, like probability of WI times probability of WI minus 1. And now this is essentially, the bigram matrix here is essentially an outer product of two vectors, which is the probability of house old and probability of house times probability of old. And this is now a rank 1 matrix because it's an outer product of two vectors. So independence corresponds to things being rank 1. But what I would really like to say is that regardless, I'm actually going to compute these bigram counts from the data. And regardless of whether WI and WI minus 1 are independent, I would like the best rank 1 approximation to be this factorization of the model. Okay? And this is actually not true under a lot of norms. It's not true under L2 or SVD, for example. But it is true under KL divergence. So if I count the bigrams from the data, these are the bigram counts, and I take the best rank 1 approximation of B according to KL divergence, or generalized KL divergence, then the resulting matrix M1 is proportional to the empirical unigram counts, where the normalizing constant is just like the total number of counts in the matrix or something. So this lets us conclude that the max likelihood estimate, or MLE unigram, is the normalized rank 1 approximation of the MLE bigram under KL divergence. And now, we used to just have the bigram and the unigram, which is full rank and rank 1. And now we can have these intermediate quantities that are low rank, somewhere in between 1 and full in our ensemble. And so in our approach, instead of just using the unsmoothed n-grams, we also use these additional low rank quantities to get intermediate levels of dependence. So next I'm going to talk about how you actually do what Dyer does and alter these lower order distributions to reflect this diversity intuition. So consider the following operation. Let B be my bigram counts. This is the row sum. So this is essentially the marginal probability of WI, because WI is on the rows, WI minus 1 is on the columns. Now consider taking B to the element y's power 0.5. So the 0 stays 0 and the 1 stay 1, but everybody else gets a square root. So the high counts actually get affected more than the low counts. And now if I take the row sum you can see that the second word, which is the most popular here, is no longer the most popular word here. Because the first row actually has a more diverse row in some sense. And so this second row all really depended on this 5, which got cut more than everyone else. And now you can take it to the extreme. You can take b to the element y's power 0. And now if I take the row sum, I get 3, 1, 1. And note this is exactly the unnormalized Kneser-Nye unigram, because this is the number of unique words that precede wi. And so in our case, power is being used as a generalization of diversity on kind of a continuous spectrum. And so we can have a similar theorem that we had before. Instead of taking the rank 1 approximation of b, we can take the rank 1 approximation of b to the element y's power 0. And this equals the Kneser-Nye unigram instead of the MLE unigram. And so now, graphically, we had a power 1 full rank bigram. I changed the color, which means I changed the power. It's still sparse. And then I can take a rank 1 approximation, and this would give me the Kneser-Nye unigram. So now, instead of just having the MLE bigram and the Kneser-Nye unigram, I can now have this intermediate matrix, which is of intermediate power, so it's a different color. And it's also low rank, so it has some intermediate level of dependence. And some people will hate me for this slide, but I really like this picture. So this generalizes to higher orders. This is the trigram. It's sparse. You can also do a special low rank approximation of the trigram, where it's still sparser than the bigram. So it's done on some slices. And then this is the low rank bigram and the unigram. And they're different colors because they're different powers and things like that. But for this talk, just for simplicity, we're just talking about bigrams. The paper has all the general theorems. So our element-wise power is essentially generalizing this count of unique histories that Kneser-Nye uses. And so what's left now is that I have all these different quantities of varying rank and power. I now need to put them together to make an ensemble that's a valid probability distribution. And the key requirements are that first, the marginal constraint must hold. So I must be able to, when I marginalize out the context, I should get the empirical unigram back. Secondly, the evaluation of conditional probabilities must be fast, just like an n-gram. So I don't want any partition functions or things like that. That would make test time slow. So it turns out that you cannot do the same thing that you can do with Kneser-Nye. You can't just subtract a fixed discount. It doesn't preserve marginal constraints, and it doesn't work out. So we have a more general two-step procedure. And if you reduced it to the Kneser-Nye case, you would get what Kneser-Nye does, but our approach is different. So first what we do is we take these powered sparse matrices. So I haven't taken any low rank approximations yet. This is the power 1, the MLE. This is power 0.5, the intermediate. And this is power 0, the binary one. And I'm going to compute certain discounts on them. And differently from Kneser-Nye, each count is actually going to get a different discount. So it's a variable discounting scheme. And on this intermediate ensemble, so this is actually an ensemble. It sums to 1. I've discounted, so it has, it is a valid probability distribution. But of course, I haven't done any smoothing. There's no low rank. But this allows me to enforce the marginal constraint on this intermediate ensemble. And then you can take the low rank approximations of these intermediate quantities, and you'll still have a valid ensemble. And there are theorems and things like that in the paper. The one slight intuition of why this works is that low rank approximations with respect to KL preserve row column sums. So here, if I discounted this matrix and it has a particular column sum less than 1, the low rank approximation will have the same column sum under KL divergence. This isn't true under other norms, but it is true under KL. And same thing with the rows. And so the discounting and the leftover weights and things like that are all preserved under the low rank approximation. This also has the nice benefit that the normalizing constants to compute conditional probabilities can also be pre-computed. Because the column sums are preserved, I can compute all the normalizers on the sparse matrix, and then on the dense matrix, I don't have to keep computing them over and over. And so this means there's no partition functions and things like that. And one of the key theorems of the paper is that essentially this preserves the marginal constraint. So in summary of our approach is essentially not only using the original n-grams that Kneser-Nye uses, It's also using these intermediate low-rank quantities that we've transformed using this element-wise power operation. And then we have a generalized discounting scheme to ensure to build the ensemble and ensure the marginal constraint still holds. So training procedure, these two things are exactly the same as Kneser and I, so they can just be computed from the corpus. The low-rank quantities, you can use alternating minimization or EM to compute the low-rank approximation with respect to KL. That's a pretty simple procedure. And one thing that's nice is that because of this ensemble representation, you don't have a very high required. The required rank is only about 100, even for billion-word data sets, which is different from like class-based methods where you have to have huge numbers of classes to be able to capture the language. Because we have this, since there's multiple elements in the ensemble, every element is doing its own thing. Okay, test time. I talked a little bit about this before, but basically, so Kneser and I is obviously very fast. It's ON, where N is the order. Our approach only has a factor of K overhead, where the K comes from having to compute an element in a low-rank diagram, I have to compute the dot product of two K-dimensional vectors, which you can do with the matrix library. Okay, so now I'll present experiments. We primarily evaluate on English and Russian. English because it's standard, Russian because it has high morphology, so it has a higher vocabulary, and so actually smoothing helps more in Russian. This is, our main baselines are different variants of Kneser and I, since that's what we're generalizing. In particular, modint can is modified interpolated, which is the state of the art. We also have some brief comparisons on like a small data set to other models that have been also working on language modeling, like class-based methods, neural nets, NP-Bayes, just to kind of give some context to what our method is doing in comparison with these other approaches. So, small data sets on perplexity. These are just a few million words. As you can see, Russian has the higher vocabulary. So this is the class-based model. This is modified, okay, back off Kneser and I, and you can see that this is the best baseline. It has the lowest perplexity. And our approach gets about 5% better on English and about 7 to 8% better on Russian. And this data set is quite popular among kind of new method evaluation. So there's lots of other methods that have used this data set. So I've done some of the methods do different preprocessing, so that's why I've calibrated everything so the raw perplexities are calibrated, so it's different from the previous slide. So this is n-grams, so this is Kn. Context size 3, so it's a 4-gram model. You can see modified interpolated is better. This is an infinity-gram hierarchical Pitman-Yor. It's basically generalizing Kneser and I to infinite context length. So you use more context size and you can gain some perplexity from that. Of course, it might be painful computationally, but our approach can actually use the same context size as Kneser and I, only 3, but it can get a lower perplexity actually than using an infinity-gram because it's using the context more efficiently in some sense by using these low-rank matrices. If you're willing to deal with partition functions, you can also use neural nets. So this is a log bilinear net from 2007 by Min and Hinton. It actually does worse. The context 5 version actually does worse than our method. The context 10 does very slightly better, about 0.9 perplexity. If you go to infinity, then an RNN can do better. So I think, obviously things depend on your application. I think our method is very good when you want a small context size and fast test time evaluation. So large data sets, these are about billion words, so they're much more realistic. This is about 1.3 million vocabulary for the Russian. And on 8 cores, our method trains on English in about 3 hours and Russian in about 7 hours. Basically, the vocabulary size matters more than the corpus size to training time. And we get similar results to what we got on the small data sets. So it's about 3% on English and about 9% on Russian. So lastly, we have a machine translation task. The language model is used as a feature in the translation system. And so our goal is to compare single language model to single language model. So we don't use like both our feature and the CAN feature. We just use one or the other. And to deal with some non-determinism, basically, the way you learn the weights uses a lot of randomness. So we actually only train the weights once using the CAN And then I use the same weight for both our method and PLRE. I mean, for both PLRE and KN. Here we get a modest improvement, about 0.16. It's consistent in the sense that if you run it 10 times, we always do better, sometimes marginally, sometimes by more. This is kind of a source of feature work. I think the way you get more blue score is to use, you condition on the source and things like that. So if we extended our model to be a bilingual model, for example, then maybe you would get more blue. So in conclusion, we presented a novel technique for language modeling called power low rank ensembles. It can consistently outperform KN baselines, and it's effective for small content sizes and fast at test time. And it's part of a broader theme of works exploiting the connection between linear algebra and probability for new solutions in NLP. My co-author has another talk later today that has different but similar theme. And thanks a lot, and the code is available online.
We have time for a few questions. Yes, please.
Thank you for a great talk. Knazer-Nye has really interesting associations with non-parametric Bayes, like the hierarchical Pitt-Manure process. Does this result give you any insights into other facts about non-parametric Bayes or related models?
Not directly. I think that you could envision it as maybe, so hierarchical Pitt-Manure, like low rank approximation is essentially like latent variables. And if maybe you could enhance that model by using some latent variables, and maybe you could get long context size as well as this kind of low rank structure that our approach has. So I think they could work in conjunction, I think, as opposed to, I think they're a little bit orthogonal because the Pitt-Manure is more used to generalize, to make it work for longer contexts. And whereas our approach is more for, more efficiently using the small context, right?
More questions? Okay, thanks again.